April 28, 1941, Newport News, Virginia. The keel of USS Essex stretched across the building way like the spine of some massive steel creature waiting to be born. Welders moved along the framework, their torches casting dancing shadows across the shipyard floor. The air tasted of salt water and hot metal, and the noise of riveting guns echoed off the James River like continuous thunder. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. James Morrison, a 37-year-old naval architect from the Bureau of Ships, stood at the edge of the construction platform with blueprints rolled under his arm and a growing knot of anxiety in his chest. The carrier taking shape before him represented something the United States Navy had never attempted. Not just one massive warship, but an entire fleet of them. 24 identical giants, each capable of carrying nearly 100 aircraft into battle, each displacing more than 27,000 tons. The problem wasn't whether America could build carriers. The problem was whether America could build them fast enough. The previous generation of fleet carriers, Yorktown, Enterprise, Hornet, had required between 3 and 4 years from keel laying to commissioning. Careful, methodical work by skilled craftsmen who understood that warships were precision instruments where every rivet mattered, where every weld had to be perfect, where rushing meant sailors dying when bulkheads failed under enemy fire. But the world was burning. In Europe, Nazi Germany had conquered France, driven Britain to the edge of defeat, and was preparing to invade the Soviet Union. In the Pacific, Imperial Japan was expanding its empire with terrifying speed, building carriers of its own. And the United States Navy, in April 1941, owned exactly 7 fleet carriers. 7 ships to patrol 2 oceans, to protect a nation that everyone knew would soon be at war. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The mathematics were brutal. If Essex and her sisters took 3 to 4 years to build, the first wouldn't be ready until late 1944 or early 1945. By then, the war might already be lost. Japan would control the Pacific. Germany might have defeated Britain. The window for American industrial power to make a difference would have closed. What James Morrison didn't know, what none of the engineers and shipbuilders gathering that morning could have predicted, was that within 3 years, Essex-Class carriers would be rolling off American building ways every 60 to 90 days, not through some individual worker's clever trick, but through a revolution in how warships were designed and constructed. A systematic transformation that would cut construction time by more than half and prove that engineering discipline, when combined with industrial determination, could accomplish what seemed physically impossible. The crisis had begun 2 years earlier, in May 1939, when the Bureau of Ships first proposed a new carrier class. The design team was led by Commander Leslie Kniskern, a methodical engineer who believed that good warship design came from listening to the men who actually operated them. He gathered input from aviators who'd landed on pitching carrier decks in storms, from mechanics who'd maintained aircraft in cramped hangar spaces, from damage control officers who'd fought fires and flooding. The preliminary specifications called for a 27,000-ton carrier that could operate 90 aircraft, steam at 33 knots, and survive battle damage that would sink smaller ships. But here was the constraint that shaped everything. The carrier had to fit through the locks of the Panama Canal. That single requirement, the ability to transit quickly between Atlantic and Pacific, set the maximum beam at 110 feet. Everything else cascaded from that limitation. The flight deck could only be so wide, the hangar could only be so large, the armor protection had to fit within weight restrictions. It was like solving a 3-dimensional puzzle where every choice affected every other choice, where adding protection here meant reducing fuel capacity there, where increasing aircraft capacity meant accepting vulnerability somewhere else. The design that emerged in early 1940 represented a careful balance of compromises. The Essex-Class would be larger than the Yorktowns, but not so large they couldn't move between oceans. They would carry more aircraft than any previous American carrier, but not so many that flight operations became impossible to coordinate. They would have better armor protection, but not so much armor that they became too slow or too expensive. Then came the requirement that would prove most important, though nobody understood it at the time. The carriers had to be buildable, not just theoretically constructible by master shipwrights working at peacetime pace, but actually manufacturable by American shipyards employing workers who might never have built warships before. Constructible in months, not years. Buildable in quantity, not as individual masterpieces. The Bureau of Ships made a decision that would prove revolutionary. They would design the Essex-Class from the beginning for mass production. The idea seemed almost heretical. Capital ships, battleships, and fleet carriers were supposed to be unique creations, each one slightly different, each incorporating the latest technological advances, each representing the pinnacle of naval architecture. Mass production was for merchant ships and landing craft, not for the Navy's most important warships. But the Bureau's engineers understood, something that tradition-minded officers didn't. In the coming war, numbers would matter as much as quality. A fleet of good carriers available in 1943 and 1944 would be infinitely more valuable than a fleet of perfect carriers completed in 1946 after the war was already decided. So they designed for standardization. The Essex-class hull would incorporate extensive use of flat steel plates, not because flat plates were ideal for hydrodynamics or structural strength, but because flat plates were easier to cut, easier to form, easier to weld, easier to inspect. A shipyard worker with basic training could work with flat plates. Curved compound sections required master craftsmen. The structural bulkheads would be positioned at regular intervals, creating uniform compartments that could be prefabricated. The electrical systems would use standardized components, the ventilation trunking would follow repeating patterns. Even the gun mounts and radar installations would use common bases that could be prepared in advance. The steel itself represented another crucial innovation. Previous American carriers had used traditional Class B armor plate for protection. Class B was effective but heavy, and every pound of armor meant one less pound available for fuel, ammunition, or aircraft. The Essex design specified special treatment steel, a nickel-chrome alloy that provided the same protective qualities as armor plate but could serve as structural material. STS could be welded. It could be formed into complex shapes. It could function as both protection and structure simultaneously. A bulkhead made from STS didn't require armor backing because it was the armor. This dual-purpose approach saved thousands of tons of weight, which translated into more fuel capacity, more aviation gasoline storage, more ammunition. It also meant fewer separate components to manufacture and install. But the most important characteristic of STS was its weldability. Traditional armor plate had to be riveted. Riveting required skilled workers, special equipment, and enormous amounts of time. Welding could be learned more quickly, could be performed faster, and created structures that were actually stronger under certain conditions. The Essex-class carriers would be the first American capital ships designed from the keel up for welded construction. Not partially welded, but almost entirely welded except for a few critical joints that required the redundancy of mechanical fasteners. On July 3, 1940, the Navy awarded the first 3 Essex-class contracts to Newport News Shipbuilding and Dry Dock Company, CV-9, CV-10, and CV-11, 3 carriers from one shipyard. It seemed ambitious enough. Then, in September 1940, 8 more contracts were awarded, 4 to Newport News, 4 to Bethlehem Steel's Fall River Shipyard in Quincy, Massachusetts. 2 more contracts followed just 8 days after Pearl Harbor. By the time America officially entered the war, 11 Essex-class carriers were under contract with more being planned. It was the largest capital ship program in history, and nobody was entirely certain American shipyards could actually deliver. The challenge wasn't just building 1 or 2 carriers. Yorktown and Enterprise had proven American yards could construct excellent warships given enough time and resources. The challenge was building 24 carriers simultaneously, while also constructing battleships, cruisers, destroyers, submarines, and hundreds of merchant vessels. The challenge was finding enough skilled workers when men were enlisting in the military by the hundreds of thousands. The challenge was coordinating production across multiple shipyards that had their own methods, their own traditions, their own ways of doing things. James Morrison's job was to make it work. As the Bureau of Ships liaison to Newport News, he was responsible for translating design specifications into actual construction procedures. The blueprints that arrived from Washington showed what the finished carrier should look like. Morrison's task was to figure out how to actually build it. He spent the summer and fall of 1941 walking the Newport News shipyard with a stopwatch and notepad, watching how work actually happened. He observed that welders spent 30% of their time waiting for cranes to deliver components. He noticed that fitting sections together required constant adjustment because tolerances weren't quite right. He saw that inspection procedures created bottlenecks, as quality control officers checked every weld before allowing work to proceed. None of these problems were anyone's fault. They were simply the reality of shipbuilding as it had always been practiced. Warships were bespoke creations. You built them piece by piece, adjusting as you went, solving problems as they emerged. Every ship was slightly different because construction was an iterative process. But Essex-Class carriers couldn't be built that way. There wasn't time for iteration. There wasn't room for each ship to be unique. The Bureau needed a system that could produce carriers like Ford produced automobiles, not identical, but standardized enough that lessons learned on one ship immediately applied to all the others. Morrison began documenting everything: the sequence of construction activities, the crew sizes for different tasks, the equipment required at each stage, the inspection criteria, the supply chain for materials. He created what would later be called a critical path analysis, identifying which tasks had to happen in sequence and which could happen in parallel. The insights were revealing and disturbing. Essex's keel had been laid in April, but by December 1941, 8 months later, the ship was nowhere near complete. At the current pace, she wouldn't commission until mid to late 1943, 2.5 years from keel to completion. Better than the 3 to 4 years of previous carriers, but still far too slow. Then Pearl Harbor changed everything. December 7th, 1941. Japanese carrier aircraft destroyed or damaged 8 American battleships, killed more than 2,000 servicemen, and demonstrated with brutal clarity that carriers were now the dominant weapon of naval warfare. Within days, the urgency shifted from important to desperate. The Navy didn't need Essex-Class carriers. The Navy needed them yesterday. Congress appropriated funds for 19 additional carriers in the weeks after Pearl Harbor. 10 contracts were awarded in August 1942, 3 more in June 1943. The total program reached 32 carriers ordered from 5 different shipyards spread across the East Coast. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. It should have been chaos. 32 massive warships under construction simultaneously, each requiring thousands of tons of steel, hundreds of miles of electrical cable, thousands of separate systems and components, shipyards competing for the same skilled workers, the same materials, the same equipment, design changes being implemented even as ships were under construction, meaning that carriers laid down months apart had to incorporate different specifications. What prevented chaos was systematic standardization. In early 1942, the Bureau of Ships made a series of decisions that would prove decisive. First, one shipyard would serve as the lead Newport News. Every design modification, every construction improvement, every lesson learned would be documented at Newport News and immediately shared with the other 4 yards. Second, all 5 shipyards would receive identical blueprints and specifications, not similar, identical. When a welder at Norfolk Navy Yard opened the specifications for a particular joint, those specifications would match exactly what a welder at Philadelphia Navy Yard was reading. Third, major components would be standardized across all ships. The Westinghouse steam turbines that powered Essex would be identical to the turbines in Lexington and Intrepid and every other carrier. The Babcock and Wilcox boilers burning at 850 degrees Fahrenheit would be interchangeable units. The 5-inch 38 caliber gun mounts, the 40mm anti-aircraft batteries, the radar installations, the catapults, the arresting gear all standardized. This required unprecedented coordination. Representatives from all 5 shipyards met monthly in Washington to share progress, problems, and solutions. When Bethlehem's Fall River Yard developed an improved method for installing ventilation trunking, that method was documented and distributed to the other yards within weeks. When Norfolk discovered that pre-welding certain bulkhead sections reduced installation time by 30%, that became standard procedure across the program. The transformation happened gradually, then suddenly. In 1942, the first Essex-Class carriers crept toward completion at what seemed like glacial pace. Essex herself was commissioned on December 31, 1942, 20 months after her keel was laid. Respectable, but not revolutionary. But Lexington, whose keel was laid just 2 months after Essex, commissioned in February 1943, just 16 months from keel to commissioning. Yorktown, the third carrier, took 17 months. Intrepid, 16.5 months. The numbers were improving ship by ship as the yards learned, adapted, and refined their processes. Then came Franklin, laid down at Newport News in December 1942, and commissioned in January 1944. 14 months. 14 months from keel laying to a fully operational fleet carrier capable of carrying 90 aircraft into combat. Newport News had cut construction time by more than half compared to the pre-war standard. The breakthrough wasn't one innovation, it was dozens of innovations compounding. Prefabrication meant that major hull sections were assembled away from the building ways, then lifted into place by massive cranes in a matter of hours, rather than being built piece by piece over weeks. Welders worked in specialized teams with precisely defined sequences, each team becoming expert at particular joints rather than being generalists who welded everything. Electrical and piping work happened simultaneously with structural construction rather than sequentially. As soon as a compartment's bulkheads were in place, electricians and pipe fitters moved in to install their systems even while welders were working on adjacent compartments. Quality control shifted from inspecting finished work to inspecting components before installation. If a prefabricated section didn't meet specifications, it was rejected before being craned into position, rather than discovered after installation, when fixing it required dismantling surrounding structure. Materials arrived at the shipyard in pre-positioned lots, delivered to specific locations at specific times rather than being stockpiled in central warehouses. This just-in-time approach, though nobody called it that in 1943, meant that workers weren't waiting for materials and materials weren't occupying valuable yard space. The learning curve proved remarkably steep. The first carrier from each yard took the longest. The second took less time. By the third or fourth, the yards had developed rhythms and systems that seemed almost impossible. By early 1944, Newport News was delivering Essex-Class carriers approximately every 90 days. Three months from keel laying one carrier to keel laying the next, with carriers commissioning in steady rhythm, Bethlehem's Fall River Yard in Quincy achieved similar timelines. The Navy yards at Norfolk, Brooklyn, and Philadelphia, though slightly slower, were still completing carriers in 16 to 20 months. The mathematics of production became overwhelming for America's enemies. In 1943 and 1944, Essex-Class carriers entered service every 2 months on average. Every 2 months, the United States Navy gained another 30,000-ton floating airfield capable of projecting power across 1,000 miles of ocean. Japan's Navy, in early 1943, faced a calculation that grew more desperate with each passing month. American carriers were appearing in the Pacific at a rate imperial planners had believed impossible. Essex joined the fleet in May 1943. Yorktown and Intrepid followed within weeks. Lexington commissioned in February. By summer, 6 Essex-Class carriers were operating in the Central Pacific. The Japanese had expected parity, perhaps even temporary superiority, while American shipyards slowly delivered replacements for the carriers lost at Coral Sea, Midway, and Santa Cruz. Instead, they confronted an armada. In November 1943, Task Force 50 participated in the Gilbert Islands campaign with 5 Essex-Class carriers: Essex, Yorktown, Lexington, Bunker Hill, and Independence, launching coordinated strikes against Tarawa and Makin that overwhelmed Japanese defenses through sheer volume of aircraft. The Battle of the Philippine Sea in June 1944 demonstrated what mass-produced carriers could accomplish when operated as a unified force. 6 Essex-class vessels participated, shooting down around 600 enemy aircraft and sinking 3 carriers, while the United States lost 123 planes and no ships. The engagement, later called the Great Marianas Turkey Shoot by American aviators, showed that quantity had become its own quality. Each Essex-class carrier operated approximately 90 aircraft by mid-war F-6F Hellcat fighters, SB-2C Helldiver dive bombers, and TBF Avenger torpedo bombers. 6 carriers meant 540 aircraft that could be coordinated into massive strike packages. The Japanese couldn't match those numbers. Their carrier force, devastated at Midway and steadily ground down through 1943, lacked both the ships and the trained aviators to compete. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the carriers themselves were only half the equation. The other half was the transformation of the American workforce that built them. In 1941, Newport News Shipbuilding employed approximately 12,000 workers. By 1944, that number had swollen to 31,000. Similar expansions occurred at every shipyard building Essex-class carriers. The workforce looked radically different from the pre-war years. Women comprised nearly a quarter of shipyard workers by 1944, performing every job from welding to crane operation. African Americans found opportunities in skilled trades that peacetime segregation had denied them. Training programs converted farmers and factory workers into shipfitters and electricians in a matter of weeks. The systematized construction methods made this workforce transformation possible. When every weld followed documented procedures, when every installation matched standardized blueprints, when quality control checked components before assembly rather than after, workers with limited experience could produce work that met exacting specifications. The prefabrication revolution proved crucial. Rather than building carriers entirely on the building ways, shipyards created massive hull sections in separate facilities. A bow section might be 90% complete, welded, compartments installed, piping, and electrical. Work finished before being lifted by enormous gantry cranes and positioned on the keel. This parallel construction meant that hundreds of workers could be simultaneously working on different sections of the same ship without interfering with each other. Newport News developed a rhythm that approached assembly line precision. Keel plates were positioned on Monday. Major hull sections were craned into place over the next 10 days. Deck structures followed. By day 30, the carrier's basic structure was recognizable. By day 60, the hull was watertight and internal systems were being connected. By day 90, the ship was ready for launch, with fitting-out work continuing at the pier for another 3 to 4 months. The learning transferred between ships. When welders on Yorktown discovered that a particular joint sequence reduced warping, that technique was documented and applied to Intrepid and every subsequent carrier. When electricians on Lexington found a more efficient routing for cable runs, those routes were incorporated into the blueprints for ships still under construction. This continuous improvement wasn't revolutionary in concept, it was simply industrial best practice applied with discipline and urgency. But the scale was unprecedented. Improvements that might have taken years to propagate through traditional shipbuilding spread across the entire program in weeks. The standardization also created unexpected efficiencies in logistics and supply. Because all Essex-class carriers used identical Westinghouse turbines, manufacturers could produce those turbines in quantity, reducing unit costs and delivery times. Each boiler room had 2 Babcock and Wilcox boilers operating at 565 pounds per square inch at 850 degrees Fahrenheit, and every carrier used the same model, allowing suppliers to maintain production runs without retooling. Gun mounts, radar installations, catapult systems all followed the same pattern. Manufacturers knew exactly what specifications were required. Parts were interchangeable across the fleet. A replacement turbine blade for Essex would fit Yorktown or Intrepid or any other carrier in the class. This interchangeability extended to operational advantages. Sailors and officers could transfer between Essex-class carriers without needing to learn different systems. A damage control team from Lexington would immediately understand the layout aboard Bunker Hill. An aircraft maintenance crew from Essex could work on planes aboard Yorktown without confusion. The carriers were, in essential ways, the same ship built 24 times. The design's ruggedness proved itself repeatedly under combat conditions. USS Bunker Hill was hit by 2 Japanese aircraft carrying bombs, explosions killing 390 crewmen. But the ship was able to return to Pearl Harbor under her own power. USS Intrepid survived being struck by 4 kamikaze pilots. USS Franklin suffered catastrophic damage from 2 armor-piercing bombs that detonated aircraft and ammunition on the flight deck and hangar deck, killing more than 800 men, yet the carrier's captain refused permission to abandon ship and brought her home. Not a single Essex-class carrier was sunk by enemy action during World War II. This wasn't luck. It was engineering. The special treatment steel that served as both structure and armor absorbed battle damage that would have penetrated conventional construction. The compartmentalization that divided each carrier into hundreds of separate watertight spaces contained flooding and fire. The redundant systems, multiple boiler rooms, separate engine rooms, distributed electrical generation, meant that damage to one area didn't cripple the entire ship. The design emphasized survival over perfection. Naval architects accepted that the flight deck might buckle in severe storms, calculating that occasional storm damage was preferable to structural weight that would reduce aircraft capacity. In June 1945, 2 carriers suffered buckled flight decks during a typhoon southeast of Japan, precisely as the architects had predicted, but both carriers remained operational. By the end of 1944, the strategic impact of Essex-class production became undeniable. In 1943 and 1944, every 2 months, an Essex-class carrier entered service to reinforce American naval forces in the Pacific, in addition to 9 Independence-class light carriers that all entered service in 1943. Japan couldn't replace its losses. America was adding to its strength faster than the enemy could sink ships. The Battle of Leyte Gulf in October 1944 demonstrated American numerical superiority with brutal clarity. 4 Essex-class carriers participated in what became the largest naval battle in history. Japanese forces threw everything remaining into a desperate attempt to destroy American amphibious forces landing in the Philippines. The result was catastrophic for Japan. The battleship Musashi, largest ever built, was sunk. 3 Japanese carriers went to the bottom. The Imperial Japanese Navy lost its capacity to conduct major offensive operations. From that point forward, Essex-class carriers operated with near impunity, launching strikes against Japanese positions throughout the Pacific, supporting amphibious landings, and eventually attacking the Japanese home islands themselves. In February 1945, carriers from Task Force 58 struck Tokyo, demonstrating that American naval power could reach anywhere in the Pacific. The human cost of this dominance shouldn't be romanticized. Carrier operations were dangerous even without enemy action. Flight deck accidents killed sailors. Aircraft crashed during training. The kamikazes that hit Bunker Hill, Franklin, and others killed thousands of American servicemen. But the alternative, a prolonged war where Japan retained the initiative, would have cost far more lives on both sides. The production achievement transformed not just naval warfare, but the entire trajectory of the Pacific War. In January 1942, after Pearl Harbor, the United States owned 3 operational carriers in the Pacific. By August 1945, when Japan surrendered, that number had grown to dozens, with Essex-class carriers forming the backbone of American sea power. The surrender ceremony aboard USS Missouri in Tokyo Bay on September 2, 1945, represented the culmination of that industrial achievement. Though carriers weren't prominently featured in the ceremony, the Navy still gave symbolic primacy to battleships. Everyone understood that carriers had won the Pacific War, and among those carriers, the Essex-Class had been decisive. The post-war period vindicated the design's adaptability. Rather than becoming obsolete, Essex-Class carriers underwent modernization programs that extended their service lives for decades. Angled flight decks, steam catapults, improved radar, strengthened elevators, all were retrofitted to handle jet aircraft that would have been inconceivable in 1941 when the first Essex was laid down. Carriers that had launched propeller-driven Hellcats and Avengers in World War II were launching supersonic jets in the 1960s. The flexibility came from the original design philosophy. Because the ships were robustly built with margin for growth, because the basic structure was sound, because the compartmentalization allowed modifications without compromising integrity, they could evolve with technology. During the 1950s, the Essex-Class underwent a series of modernization schemes, with most carriers serving as attack aircraft carriers and some later designated as anti-submarine warfare support aircraft carriers. They served in the Korean War, earning additional battle stars. They operated during the Cuban Missile Crisis. Multiple Essex-Class carriers saw combat in Vietnam. The final Essex-Class carrier, USS Lexington, wasn't decommissioned until 1991, serving her last years as a training carrier. 49 years of service, from a design that entered the war before jet aircraft existed, before nuclear weapons, before guided missiles, before all the technologies that would define late 20th century naval warfare. 4 Essex-Class carriers survive today as museum ships: USS Yorktown in Charleston, South Carolina, USS Intrepid in New York City, USS Hornet in Alameda, California, USS Lexington in Corpus Christi, Texas. Visitors walking their decks can see the flat steel surfaces that made rapid construction possible, the special treatment steel that protected them in combat, the hangar decks where prefabricated sections were assembled. The lesson of the Essex-Class extends beyond naval architecture and shipbuilding. It speaks to fundamental questions about how complex systems can be designed for rapid production without sacrificing quality. The traditional approach to major warships treated each one as a unique creation, built slowly by master craftsmen using methods refined over decades. That approach produced excellent ships, but it couldn't produce them fast enough when war came. The Essex-Class designers made different choices. They accepted constraints that earlier naval architects would have rejected: the limitation of fitting through the Panama Canal, the extensive use of flat plates instead of optimal hydrodynamic curves, the standardization that meant every ship was essentially identical. They designed for manufacturability from the beginning, understanding that the best design was worthless if it couldn't be built in time to matter. This required humility. Engineers had to admit that perfect wasn't necessary if good enough could be delivered in half the time. Shipyards had to accept that traditional methods, however honored, needed change. The Navy had to trust that systematization and standardization could produce combat-effective warships. The gamble succeeded because everyone involved understood what was at stake. In 1941 and 1942, American defeat in the Pacific was a realistic possibility. Japan's early victories demonstrated that motivation and tactical skill could overcome material disadvantages. The window for American industrial power to make a difference was narrow. If carriers couldn't be delivered in time, in sufficient numbers, then all of America's industrial capacity would be irrelevant. James Morrison, the naval architect who documented construction procedures at Newport News, retired after the war without public recognition. The thousands of workers who welded, fitted, installed, and inspected components on Essex-Class carriers went back to civilian life, their contributions recorded only in employment records and shipyard photographs. But their collective achievement reshaped not just naval warfare, but the fundamental understanding of what large-scale industrial production could accomplish under pressure. The transition from 3 to 4 year construction times to 14 to 20-month timelines represented a systematic transformation, not a single breakthrough. It was the compounding effect of hundreds of improvements, each individually modest, combining to produce results that seemed impossible when the program began. The arithmetic of those improvements wrote the history of the Pacific War. 24 carriers commissioned. 17 commissioned during World War II, with 14 sailing into combat zones, amassing 88 battle stars, thousands of aircraft launched, millions of tons of bombs and torpedoes delivered, Japanese positions neutralized, amphibious invasions supported, enemy fleets destroyed. Each statistic represented thousands of workers in American shipyards, following procedures, checking quality, solving problems, improving methods. The victory wasn't won by individual genius or breakthrough innovation. It was won by disciplined engineering, systematic improvement, and the determination to prove that democracy's industrial power could outproduce totalitarian enemies. The rejected idea that never existed, the individual worker's breakthrough that transformed production, makes for compelling drama. The truth is more instructive. No single person cut construction time in half. The entire system did. Engineers who designed for manufacturability, managers who documented and shared improvements, workers who executed procedures with skill and dedication, suppliers who delivered standardized components on schedule, naval officers who trusted that systematic methods could produce combat-effective ships. The Essex-Class succeeded because everyone involved accepted that the best solution was the one that worked, not the one that satisfied traditional notions of how warships should be built. That willingness to abandon tradition when circumstances demanded it, that capacity for systematic innovation under pressure, proved more decisive than any individual breakthrough could have been. 24 carriers, built in 3 years, forming the backbone of American naval power through 5 decades of service. The achievement stands not as a story of individual heroism, but of institutional capability, of what can be accomplished when complex organizations align around clear goals, document their methods, share their learning, and refuse to accept that traditional timelines are immutable. The Essex-Class carriers rolled out every 60 to 90 days in 1944, not because someone had a trick, but because thousands of people built a system, and that system, more than any individual innovation, won the war. The contrast between 1945 and 2025 could hardly be more stark. In the final year of World War II, the United States Navy commissioned multiple Essex-Class carriers within months of each other. Today, a single Gerald R. Ford-class supercarrier requires approximately 5 years from keel laying to commissioning and costs over $13 billion. The Ford-class carriers are technological marvels, nuclear-powered, equipped with electromagnetic catapults, advanced radar systems, and capable of operating for decades without refueling. They represent the cutting edge of naval engineering. But they also represent a construction paradigm that is the opposite of what made the Essex-Class possible. Modern supercarriers are bespoke creations, each one incorporating the latest technologies, each one slightly different from its predecessors as systems evolve during the lengthy construction period. The Ford-class construction timeline means that decisions made in 2015 affect a ship that won't be fully operational until 2025 or later. Technology advances during that decade. Threats evolve. Strategic requirements change. The Essex-Class succeeded because it accepted good enough, delivered quickly rather than perfection delivered slowly. Modern naval construction has optimized for perfection, for technological superiority, for individual ship capability. The cost is time and numbers. The United States Navy operated 24 Essex-Class carriers in 1945. Today, it operates 11 supercarriers total. It would be difficult to imagine today's industrial base building that many carriers in such a short amount of time. The shipyards that built Essex-Class carriers have either closed or consolidated. The workforce that could transition from automobiles to warships in months no longer exists in comparable numbers. The supply chains that delivered standardized components on schedule have fragmented across global networks, but the fundamental lessons of the Essex-Class remain relevant. When the Bureau of Ships designed for manufacturability in 1940, they were making explicit trade-offs: flat steel plates instead of optimal curves, standardized components instead of customized perfection. documented procedures instead of master craftsmen working from experience. Each trade-off sacrificed some theoretical optimum in exchange for practical buildability. Modern military procurement often makes the opposite choices. Requirements documents specify cutting-edge performance in every dimension. Contracts reward technical excellence over producibility. Development timelines assume that years of refinement will yield superior capabilities. The result is weapons systems that are individually impressive but difficult to build in quantity, expensive to maintain, and slow to deploy. The Essex-Class approach suggests an alternative. What if major weapons systems were designed from the beginning for rapid production? What if standardization and interchangeability were primary requirements rather than afterthoughts? What if good enough available in 2 years was valued more highly than perfect available in 6? These questions aren't hypothetical. They're increasingly urgent as strategic competition intensifies. Reviving the Essex-Class spirit of rapid production and strategic vision could help the United States build a fleet capable of countering threats in the Indo-Pacific. The challenge isn't technical American industrial capacity, though diminished from World War II levels, remains formidable. The challenge is institutional and cultural. Military procurement culture has evolved to minimize risk by maximizing capability. Every new ship must be better than the last. Every system must incorporate the latest technology. Every requirement must be met or exceeded. This approach produces excellent individual platforms, but struggles to produce them in sufficient numbers to achieve strategic effects. The Essex-Class demonstrated that strategic effects come from adequate numbers of good platforms more reliably than from small numbers of perfect platforms. 24 Essex-Class carriers overwhelmed Japanese naval aviation, not because each individual carrier was superior to Japanese counterparts, but because 24 carriers could be everywhere simultaneously, could absorb losses and continue operating, could experiment and iterate and learn faster than any opponent. The operational flexibility of standardized platforms proved as important as their technical capabilities. When USS Franklin was catastrophically damaged in March 1945, her air group transferred to other carriers in the task force and continued operations immediately. The ships were similar enough that pilots, maintenance crews, and support personnel could function effectively on any Essex-Class carrier without extensive retraining. Modern supercarriers lack this interoperability to some extent because each one is unique. The Ford-class incorporates systems that earlier Nimitz-class carriers don't have. Even within the Nimitz-class, ships completed years apart have different configurations. This individuality means that crew transfers require retraining, that spare parts aren't always interchangeable, that lessons learned on one ship don't always apply directly to others. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.